raise your hand? Okay, good. Beautiful. Okay, beautiful lecture hall. I want to thank very much everybody who's spoken, including Professor Roy, for putting a lot of this together. It's a lot of work. I really appreciate that. I've run about 8 or 9 international meetings myself, and it's always nervous through the first night, moving people around and the talks and the meals and so on, start gelling that people know what's going on. I appreciate Dr. Roy's introduction. He covered some of the points that I was going to make. And I look forward to the coming days of chemistry and biology and photochemistry and green energy and material science with you as if you think that I can be insightful or helpful. So I'm going to move through a series of topics that my group has worked on. This is funded by these agencies and some international agencies and industry. So it starts out really logically with an overview. But as per one of Professor Roy's comments, the area of POM chemistry, which is today really POM science, because it's so broad, covers so many areas. And it impacts many other materials, it impacts techniques, it impacts several issues of national priority. One of them, of course, is solar fuel, but many others. And so even though the core community is not that large, there's nearly 200 researchers or groups or companies that have used POMs around the world fairly recently. The logical thing is to kind of give an overview of some of the highlights. I can't cover everything. I would say, though, that as you work with me and listen to these lectures, if there's a specific area that's of interest or it's not clear, I'd like to know about it, and then I can move from there. I apologize, I've only had 2 hours sleep and I'm jet lagged, but I feel fine. I'll do better as the days go on here. That's, as most of you know, that's just the way international travel is. So what I thought the logical topics, these are very general ones, are shown here. I'll make, in addition to showing some general points, then I'll talk about how POMs are made. There's kind of 2 different philosophical approaches. Then I'll talk about geometrical and electronic structure. So geometrical structure is just where the atoms are. So that's what you get from crystallography. Single crystal XRD, X-ray diffraction, or powder X-ray diffraction, PXRD. Electronic structure, where the orbitals are, where the electronic states are and their energies. And these are both very important in every aspect of science, not just catalysis, not just medical applications, not just solar fuel splitting devices, and on and on. It's a core of much of the way we think and the way we create, the way we think broadly and in an innovative way. Then we'll talk about some reactivities and then applications. So applications, because these compounds are so extraordinarily rich. I mean, we do work on other molecules, but I just don't know any other class of molecules that approaches POMs, polyoxometalates, and their diversity and their potential utility. We work with MOFs and a number of other things, but it's POM chemistry, now like POM science is just extraordinarily rich. Okay, so let's just start with some comments about the structures and what they are. So depicted here is the common Kagan structure, which has the central atom and then 12 metals bridged by formerly oxide, oxygen 2- ions. And you can depict structures in many ways. This is popular in organic and biological chemistry. You look at the atoms and the bonds are sticks. This is very popular in material science and solid state chemistry. It's where you have the silicon polyhedral notation. So each of these octahedra has a metal in the middle, and the vertices are oxygens. And then the Kagan structure has a tetrahedral unit in the middle, XO4. So the central atom can be about half the periodic table. So it's an extraordinarily diverse set of compounds just with the Kagan structure. And the Kagan is one of hundreds, probably over 1,000 structures now. Even though building blocks in this are found in many other POMs, and they're also found in solid-state materials of many kinds, including ones that are very important technologically right now. And that gets to a key point that polyoxometalates, in one sense, are molecular analogs that you can study of metal oxides or extended solids. Very hard to study extended solids. Most of the activities on the surface, whether it's photoinduced or dark, and it's really hard to know exactly the geometrical electronic structures of the surface. You don't know where the atoms are in the orbitals. With POMs, you do. You calculate it straightforwardly with DFT and other methods. You can do molecular dynamics and get other information out. So there's huge advantages to having a molecule. You can also do NMR. It's soluble, so you can do solution NMR. Solids you can't. You can do solid-state NMR, but that's a much more involved technique. Okay, so moving on. Just a general slide I've used for some time now about polyoxometalates. So one way to think about them is that they simply represent a midpoint in hydrolytic equilibria. And you get these polynuclear condensed species, metal oxide clusters, as shown below, they're anionic, with certain elements, specifically molybdenum, vanadium, and tungsten. And now in recent years, niobium and tantalum are getting much more interesting, primarily because they're highly basic. They have much less redox camp than the vanadium and the tungsten and the molybdenum analogs. So I think the way to think about this, and again, I will be going into kind of more detail in a lot of these things in the following discussions or lectures with you guys. And I just want to keep it informal, and if you have questions, it's good that you ask them. I can take it and still stay on time, I hope, and not bore everybody else. It's good to have an interactive four-player dynamic during the lecture. So one way to think about it is if you can take a monomer like tungstate, WO42-, so it's just a monomer meaning one tungsten. And the way you get POMs is you protonate one of the oxygens. So that's the way you activate biological molecules, carboxylic acid esters, amides, on and on and on. Here we just have an inorganic analog. So you're protonating an oxygen. That induces the formation of a bond to another metal. So you get a mu oxodimer, meaning two metals are breached by oxygen. So it's a protonation, condensation, dehydration. You're losing water. And if you continue this, you get metal oxides, which is the Earth's crust. The dominant ones are silicates and iron oxide at the transition metal elements. That's what we step on. Here in India, here in Nepal, top of Mount Everest, whatever, Tibetan Plateau, North America, we step on metal oxides. We're in an oxidizing world, so almost all the elements are present as oxides. So you usually go this way with acid, and that means that implies you can go the other way with hydroxide. You can break up POMs. So you can go from solids to POMs if you have these few elements, and you can go further with more base all the way down to monomers. Now here's the key point. We'll talk more about how this happens and aspects. But the key point is that under some conditions, this can be in equilibrium. So a lot of people in all of the chemical sciences and biochemistry think in a singular way. They construct a molecule that's going to have a certain task or function, and they don't think about it being in equilibrium with other species. But often they are. You can have different forms of enzymes, for example. Well, POMs can be rendered in equilibrium with metal oxides or monomers, depending on conditions. And sometimes that's very advantageous. So you can make a very intricate molecule with a specific function. Say it's chiral, so it's going to recognize a certain protein or inhibit a virus capsid or whatever. But you can also have it in equilibrium with other species. And you can have it, if you have an equilibrium, you have a mixture of POMs. So you can have one doing something, one job, and other POMs or metal oxide particles doing another. That's one reason why POMs are indeed as rich as they are. So again, the Kagan structure, shown here, the most studied, the most common. This is why I think they're becoming more and more popular. They're compatible there in water, so you can do green catalysis. Everybody wants to work in water, not organic solvents. And if you want to do oxidations, there's no better oxidant than air, oxygen. Number 2 is hydrogen peroxide. And that's been a huge area for 30 years. It's rather mature, but there's still interesting catalysts that come up periodically. And it's selective organic oxidations. And you can scale these. They're quite non-toxic and they're quite inexpensive. Molybdenum and tungsten are not expensive, vanadium is cheap. Niobium and tantalum, maybe a little more, but they're all inexpensive. But you know, I'm kind of in academia, whatever. I've worked with a lot of companies, and I've been involved in startup companies. That's also something that Shlomo Roy indicated that there might be interest here is to talk about when you get through all this science and medicine and technology. If you're interested in what a startup company is all about, what you have to do, what are the issues, I'll be happy to talk about that. I've done it many times. I've got 42 patents in different areas. They don't get much attention though, because the best work is usually the hardcore stuff that gets into JACS or on Monthly or whatever, Nature and Science. The nice thing about POMs is that, apart from being soluble, is that you can manipulate their chemical structures very easily. That means you can control all these properties which are important in almost every application out there, from antiviral chemotherapeutics and anti-cancer drugs to making solar fuel. Okay, so here's just a summary of some of the applications and use of POMs, polyoxometalates. So catalysis, as Shlomo had indicated, is a very big area. There's both heterogeneous and homogeneous catalysts that are either acid catalysts or oxidation catalysts. There's actually about 7 reactions that have been commercialized. These make hundreds of millions of dollars a year. I think in aggregate probably over $1 billion a year now. Just a catalysis, often of hydrocarbons, but other things as well. There's also photocatalysis, which we've done a great deal with. And now I kind of left the field, and as Shlomo says, a lot of people are starting to be interested now. I'm happy to talk about that. I actually don't have many slides on that. So there's applications in medicine. This is HIV protease, one of the key enzymes in HIV. And you can inhibit it with POMs. That's the active site where the protoprotein goes in and it gets chopped up by this enzyme. And if you put a POM with a high negative charge, it sticks on the shoulder and basically gives the thing rheumatism or arthritis. And it can't move properly, so it inhibits the enzyme. So there's a lot of interest in energy storage, not just green energy generation. People are using MOFs for that. I don't know if they're particularly promising right now, including our own work. But a lot of people are using POMs as nodes in MOF construction, metal organic frameworks. And that's a logical thing because POMs, in a sense, are a multi-dentate connector. You can have a POM with several different spikes coming out going in different directions. It's also tunable. The structures are tunable, as Shlomo Roy had indicated. So again, there's a lot of diversity there. There's some redox active MOFs where the POM part, which is the connector, it has controllable redox chemistry. Then there's kind of functional interfaces, including photovoltaics and other materials. There's the whole area of molecular electronics, which is kind of one area we haven't worked in. There's a lot of very nice work going on in Europe on that. Anna Proust in Paris is one of them. And then there's solar fuels, and solar fuels is one of the most active scientific research areas today for kind of obvious reasons, but I'll go through that. I've had real problems with the internet since I got to India. I've been here long, as I say, 2 hours sleep. So I wanted to continue this on, but I couldn't log on time. But this was the production of POMs. This is PM citations per year going up, but the numbers continue on up to 2017 at present. So, you know, they're rapidly growing in popularity. I mean, a lot of things in science and medicine have this trend, but this is a steeper trend than most. Other areas like MOFs are continuing to go up, but they're kind of they're starting to plateau. And there's things like buckyballs, fullerenes, which won the Nobel Prize 20 years ago, or whatever, not quite that one. And they were kind of very, very popular for a while. So citations went up and then dropped off. Okay, there's still a fair amount of fullerenes, but it's way down from the peak. There's no peak in the use of POMs or MOFs for that matter. The MOFs are starting to plateau. Okay, let's talk about synthesis of MOFs. And keep in mind just the extraordinary versatility of these, but also that they really are kind of molecular metal oxides. Molecular, that means you can study them. You can do NMR, you can be visible. Many techniques that you just can't do on solids. So we did this work in '99 because it was kind of a pioneering study at the time, and this was part of a technology that led ultimately to a new way to convert trees into paper without pollution, which was a multinational, multi-corporate, multi-institution effort. And so we wanted to make this POM here. So it's one vanadium that we substituted for one of the tungstens, because we thought that would oxidize wood, basically wood or wood pulp, selectively. So what you want to do is you want to oxidize the lignin in wood and leave the cellulose. Paper and many other things around us are cellulose, and that was our target. So what we did is we wanted to make it and make it isomeric here. So we went through 5 steps, and it took Jennifer Cowan, my grad student back in the 90s, about a year and a half to do that. So this is a conventional way to do synthesis. It's serial, meaning one thing after the other. And it's kinetically controlled. So each of these products that you get them because they form the fastest. There's very little equilibration here. And that's a very powerful paradigm throughout biology as well. There's some equilibration biology like membrane formation, but a lot of self-assembly is kinetically controlled, not thermodynamically controlled. It took a year and a half to do this. Then we got smart. POMs, one of the beauties of them is that they're robust. You know, why don't you just mix those elements in the right ratio? 1 aluminum, 1 vanadium, and 11 tungstens in hot water, and boil the hell out of it. So we did that, and we got this in half an hour, not a year and a half. So that's a thermodynamic synthesis. Now, most people don't do that because they don't have practicality in mind in most academic labs. We had practicality in mind here because we wanted something that was extremely robust that we could use as a selective oxidant of the lignin in wood, or biomass. Okay, and just to show this, so you can take a POM and take some of the atoms out, like one atom, tungsten with its oxygen. That's 4+, tungsten 6+, and oxide 2-, so a WO is 4+. So when you remove it, you leave oxygens on the POMs that are much more negative, so they're more reactive. And you can put other metals in here. This is the green octahedral nickel 06 units. This is made by Eugenio Coronado in Spain initially. We made this, a manganese kind of bent Big Mac. If you know McDonald's, there's the Big Mac has 2 slices of meat, right? This has 2 slices of transition metals in it, namely MO6 units. And it's bent, so the bent Big Mac, that's what my group called it. And then this is a giant nanowheel, which is just a cyclic tetramer of P2W12. So you take that 4 times, you get P8W48. And many people have done beautiful work with this, including Uli Kortz in Germany. We're making some derivatives of this that we think will be potent hydrolysis catalysts for cleaning up the environment. And you can have other synthetic units. So just a couple examples from work that we did a while ago. This particular complex has 3 irons in a sandwich form. It's a very good catalyst. You can, for O2 oxidations, various kinds. You can also make POMs chiral. Okay, there's different ways you can do that. You can use spontaneous resolution like Louis Pasteur. And if they'll crystallize in a chiral space group, then the whole crystal is one hand. It's an enantiomer hand. It's like your right hand. You can have chiral molecules that are not in a chiral space group, then they're racemic. You have equal amounts of left and right hand, right? So those are less useful. So that's spontaneous resolution. And the other thing you can do is put something, bond a organic molecule covalently. This is tartrate. And when we did that, the chirality in these carbons here extended this rather large POM, and the whole thing became handed, or chiral, and enantiomer in that case. we made the other hand with the other isomer, the enantiomer, and so then we ran the CD and we got mirror image CD spectrum. Okay, now when you add redox chem to POMs, you open up another huge experimental space. Schulman-Roy had indicated this indeed. So Achim Mueller started this kind of sub-area with the synthesis of, he just took of these giant polymolybdates. So he just took reducing conditions in acid, which in this case vanadate and molybdate, and he got this enormous compound here. That's the formula. It's a nanocapsule. It's, quote, hollow, except of course it's not. It's got counterions in the inside and bridging things like sulfate. It's extraordinarily diverse synthetically. That's the formula. All of these people, including our group and Shomo, have worked with these. They're very rich. They're kind of not terribly useful yet. I don't know any applications that are seriously interesting. But they're beautiful. They're objects of beauty. And I think they grace the covers of more chemistry journals than any other type of molecule. Because editors like big, pretty molecules like Achim's nanocapsules. Okay, this is one that we did with Paul Kugler and Botan Botar, who both worked with Achim and